All right, here is section 4.0, and I want to give you a couple of missing theorems. I'm not sure why they're missing. They do in remark 4.04, point 4. They do mention that if we think of our row operations as multiplying by matrices, they do mention the determinant of Eij times A is negative determinant of A, and they say that determinant of Ei of t times A is t times the determinant of A, and then finally determinant of Eij of t times A is just the determinant of A. Now this hints at something. So we see some matrix multiplications. Well, let's look at, if I take the determinant of Eij, well, remember that Eij is simply two rows of the identity swapped. Well, the determinant of the identity is 1, and so if I swap two rows of that, this is the minus the determinant of the identity, and so that's -1. Okay, similarly, the determinant of Ei of t, well, what we did there, right, is that we just took the ith element in the diagonal of the determinant and multiplied it by t. And so we really just took a row of the identity and multiplied it by t. So that's t times the determinant of the identity, but the determinant of the identity is 1, so that's t. And then determinant of Eij of t, well, remember that Eij of t, that is a matrix that's the identity with then a non-zero element either in the upper triangle or the lower triangle. So it's a triangular matrix with all ones down the diagonal, and so its determinant is 1. And so as we look at all these, what we see is that the determinant of Eij times A is the determinant of Eij times the determinant of A, and similarly for these others, the determinant of Ei of ta is the determinant of Ei of t times the determinant of A, and the determinant of Eij of t times A is the determinant of Eij of t times the determinant of A. Now, remember that we can write matrices as the product of these row operations. Okay, and well, definitely, so non-singular matrices we can write as products of these row operations. And so what this leads to, now it takes a bit to actually do the proof, but what this leads to is that a theorem that they've left out, which I think is a very important theorem. The determinant of A times B, that product, is the determinant of A times the determinant of B. And again, that proof for non-singular matrices, if A and B are non-singular, the way that proof works is you write A or B, either one, as this product of row matrices, and then those all behave with these theorems here. Okay, so that is how you get at this product. Now, if A or B is singular, well then the product is singular, and if A or B is singular, one of those two determinants is 0, and of course AB, if it's singular, its determinant is 0. So you just handle singular and non-singular matrices separately, but for singular matrices it falls out very easily because you get 0 equals 0. It doesn't matter if one of the two, either A or B, is non-singular, because the other makes the 0. Okay, so that's a theorem. But then from that theorem, what we have is that if, well, here's another theorem, missing theorem. If A is non-singular, and we saw a little hint of this with the cofactor and adjoint stuff, but if A is non-singular, then the determinant of A inverse is equal to 1 over the determinant of A. Okay, now that is a pretty simple proof, because, if we take the determinant of I, which is 1, so we'll say 1 here, that's the same thing as the determinant of A inverse times A, determinant, which is equal to the determinant of A inverse times the determinant of A. Kind of ran out of room there. But now, just divide both sides by the determinant of A, and we get that the determinant of A inverse is 1 over the determinant of A. So I think those are pretty important theorems. I'm not sure why they're left out. Maybe we'll find them later in the text, but these are biggies, and we do want to know these theorems. So we want to know that the determinant of the inverse is just 1 over the determinant of the original matrix, and we get that from this product thing. Determinant of A times B is the determinant of A times the determinant of B. So there are our missing theorems that I wanted to make sure we added.